I hope I can make this video very clear. So apparently this video will talk about introduction to Coloumb damping. So what is actually a Coloumb damping is that from Wikipedia, it's a type of constant mechanical damping that involves sliding friction. As you can see, when you pull this mass in this direction, okay, when you pull it here, the spring will pull this mass back. So there's a sliding friction over here, right, along the floor itself. So this is why we're talking about sliding friction, dealing with Coloumb damping. So once we talk about Coloumb damping, we're talking about sliding friction. So what is it that we are actually looking into is that for example, if you were to pull this mass in this direction and if you let it go, you oscillate, you know. So it will slowly oscillate back to this to the system. Um, e Without regarding that there is any air resistance, like we're just purely looking at the frictional force. Okay, the frictional force. When the mass is moving across the friction between the mass and the floor itself, the surface of the floor. So when you were to observe it in this trend, the x itself, as you can see, is the distance between this horizontal line. I mean, it's just this x lah. Okay, this whole thing is the x-axis, so it's moving. It's totally different from the when you hang here and then this is x. This is totally another scenario. Okay, so they are not related. But however, the graph itself is also plotting in terms of time and x. So the graph itself, the x and y axis is the same, just that now we are talking at a different x. Okay, so we're talking about this x. And then what other stuff I need to, okay, so we're actually deriving an equation for 4f over k, where this 4f over k is a value that proves that every amplitude, okay, from this point to this point, okay, for every cycle, there is one cycle back here, okay, one cycle back here. It's the difference between two cycles is 4f over k. Okay, the difference of amplitude between two cycles, okay, between this point and this point is 4f over k. I mean, sorry, between one cycle, sorry. So apparently, the amplitude between this point and this point within that one cycle is 4f over k, and then another cycle is also another 4f over k, and another cycle is another 4f over k. So we're going to prove that. And therefore, just as I said earlier, we are talking about non-homogeneous equation, and then why you are talking so much rubbish over here? So because this is Coloumb damping. Coloumb damping you can derive using non-homogeneous equation. So as we can see, in the previous videos, we are talking about a lot of differential equations. So definitely, we are also talking about differential equation in this system. So one thing to let you take home is that the Coloumb damping is due to sliding, okay, sliding friction, and then the drop of the amplitude is 5 over k for only Coloumb damping. For other damping, the drop of amplitude should not be 4f over k, I think, but whatever. So with this said, I think I'll just continue next video. So this is a very quick introduction to whatever things that is. Yeah.